I'm sure. Okay, you can see let me bring out the PowerPoint. You can see the slide.
Not yet.
Hello?
Not yet.
Okay.
I cannot see the slide, Peter.
Yeah, we can see you, Peter, but not the slide.
Okay, you're seeing. Yeah, that's weird because I see on the showing side, it is saying the screen that I'm sharing here is the one. I mean, which one you're seeing anyway?
I can see a webcam. I can see you.
Are you?
I don't see anything.
Are you seeing a blank?
Okay, now it's okay.
Okay, let me.
And now it's gone.
Off and turn it back on. Yeah, just turn it off.
Okay.
It's back on now.
I can see the BDI Tech Talk slide. If you can go into full screen, that'd be better.
Oh yeah, so that's the one. Good.
Yeah.
Actually, yeah, let me do that. Actually, on my side, I think there's a little bit networking webcam just to save the bandwidth. Hopefully that'll be better because I can hear myself with but if you guys have trouble, it looks like you're okay, right?
Mostly okay. You're
so let's get started.
Occasionally, but it should be okay. Let's go.
Okay. So yeah, so this will be as Wintao mentioned, this will be a tech talk on the machine learning representation, and the so-called representation here is really one of our early effort to try to the idea about how we approach the purpose of the implementation is really to try to give the folks who are new to machine learning so yeah, if you're an expert on machine learning, you do a lot of project, this may be this information may not be suitable for you, but I'm hoping this is useful for folks who actually really want to get started and I will also use the opportunity to introduce a few tools and technology we use here. So hopefully that's useful. So this is actually one of the projects we conducted before the hackathon, and later on we also make it we did some further development and make it a part of the my hackathon. So the slide here I'm just copy from there. So quickly, let me do a quick introduction on, to tell you guys what we're solving here. So as most of you guys know, right, with one of the flagship product of the GoToMeeting product, or with JoinMe.me, one of the common user pain point is in all this meeting product, and it's actually not just GoToMeeting, is the auto feedback scenario, right? You have this really pitch, when you have multiple people in a conference with multiple GoToMeeting devices joining the same meeting. All these devices are playing the sound against each other, and you got and it's very annoying. And similarly, there's a similar problem, but it's a different scenario. It's called audio, right? You basically hear the sound of repeating itself. So they are generated in about similar way, with multiple audience in the same conference. So really annoying. I'm pretty sure almost a single day, right? And how do we solve it today? We pretty much have no way to do it other than just use it to tell folks on the line to turn off your speaker. Sometimes people who are really new to the product, that you really need some experience to manage this. And folks who actually have I heard something from the audience. Any questions or some issues?
I think
Are we
Peter,
okay?
you are sometimes you are breaking up quite
Hey,
often.
Wintao and Tusha.
Yeah, Peter, can you hear me? Peter?
Okay. Yeah, that's why I worry. Yeah, I can hear you, but that's what I worry. It looks like there's some issue with my audio on my side.
Yeah, the audio quality is not great. Bangalore folks have some chat in the chat window saying that, and I also hear you break up once in a while.
So let me do this because well, yeah. So I will just quit the meeting and just come back again. That may be better. Okay.
Okay. All right. I'll give you a minute.
Can you hear me?
Yeah. Go ahead.
Yeah, I will do that. Okay. Yeah.
All right. Well, we'll give Peter a moment to rejoin the meeting. Sorry for the hiccup.
No worries. We just have the teaser. We just need to wait for the real thing now.
Exactly. So now you hear, you heard about the problem. We are holding a solution for you. So. Hey, thanks, Madhu, for joining. Hopefully, we can make this one useful for you guys.
Yep.
Peter, are you back?
Hello.
All right.
Yeah, I'm back. This
Not really. Still.
No, it's still not better. I can see.
How
Do you want to dial in, Peter?
Try dialing. How about it? You send me your slides. I'll present.
Okay. Using a phone. Let me.
Peter, can you send me your slide?
Okay. Okay. Do that. Okay. Yeah, I can do that.
All right.
That's a bummer. Okay, I send you a slide, and I'm going to make a phone.
Yeah, just dial in from PSTN. All right. Hold on, guys. I'm trying to receive email from Peter. Okay, sorry for the delay.
Hello.
Yeah. Oh, it's better.
Okay, I just joined again through my cell phone. So hopefully, is that better?
It's much better.
Okay.
But I have not received your slides yet. That's a problem.
I already sent it, so let me double check. It says, yeah, it didn't really, maybe something wrong with my network or something. It's still not sent. Yeah, it is sent now. You should have it.
All right, I got it.
You got it? Okay, good. So if you can present, and I have to give you instruction on the, the wiki page, the product page we're going.
Yeah, just
hopefully.
Okay.
Hopefully that's okay. Yep. So.
All right, can you guys see the slides?
Great. Yep.
Cool.
So yeah, if you can turn into a presenter mode, make it bigger.
Cool.
Sorry about that, guys. This is I don't really see this very often when I have meeting at home, but somehow something wrong with network, I guess. So yeah, so let's just continue the BDI talk. So yeah, as I mentioned earlier on, right? Today we really doesn't have a good way to solve this. And yeah, next slide, please. Went out. Next slide. Yeah. So yeah, so we we decided to give it a try with the machine learning, and really the rationale comes from this kind of thinking, right? As just a little bit of background how machine learning works for folks who haven't done this before. One of the reasons we think we could have a decent shot at this problem with the machine learning is based on the observation that this is a really annoying problem, even though it's pretty difficult from a digital signal processing point of view. That's one reason we don't have a solution, right? We don't really have a way to do this reliably by looking at the signals from audio engine and somehow suppress that. It is somewhat technical challenge over there. But we figured we have a decent shot at this problem with machine learning because it is the detecting the presence of the feedback and echo in the audio stream is actually a really simple problem for human beings, right? Like you and me, when we're on a meeting, when we hear the feedback or we hear the echo, there's no doubt we can figure it out, right? We know that it is present. So the observing that, usually is anytime you see something like this, like that can be complex by writing code to deal with that, but actually pretty easy for human to figure it out. It is, there's a decent chance that can be a good candidate for machine learning. And this is illustrated in many different places. Like you see a picture of a dog or a cat, you can always tell that, right? So having an image recognition to figure out, whether the image is a dog or a cat, it's a very good machine learning problem, and we have a very good solution for that. And in this case, it is similar. And that's how we come to this, we even initiated this effort to even bother to give it a try, right? So that said, let's see how we're doing it and how we're using machine learning to solve this problem. So this slide just give you a rough idea, as in general, any machine learning project, that generally you went through this process. You collect the data. You want to make sure you have data. All machine learning is really about using data to train the model, to create a model, and then come up with prediction, right? So first of all, you collect data, and then this is the part of it where you have to be really creative, which is you pick out the creative, the predictive features that can from the data that can be used to predict your target state. And in this case, the target state is we want to predict the audio wave, whether it's a feedback sound or whether it's a normal sound, right? So the third step, obviously, now that you got a feature, you got data, you either create a model and you train it, and then you see how good you're at it, whether the model can be accurately predicting the target state you're looking for. So, as part of this effort, once we got it done well, we integrated with the audio engine, and we did some proof of concept, application integration effort to see whether it works well for the applications. So next slide, please. And for folks on the call, if you have any questions, feel free to to ask on the fly. We don't have to wait until the end of the presentation to do a Q&A.
In the previous slide, it's not sure whether the solution is obtained or is it just we are displaying to the end users that there is an issue.
Well, we haven't really gone too far. The reference implementation is mostly focused on the machine learning, implementation. We haven't really go too far in terms of integrating the prediction with the audio engine, such that it delivers the direct benefit for the customer yet. We did some proof of concept, during the hackathon week, but as of today, we haven't really get any additional like experience improvement development to take advantage of this effort yet.
Okay, thanks.
So Wintao, next slide. So yeah, so before I go to detail about how this project works, in this, I'll spend some time later to walk through the project with you guys. This is a quick rundown of the performance, right? To see how this works. So we with the data that I mentioned earlier, and we're lucky we actually got a pretty cool model. We developed a model, and we got a really decent result. So basically, this slide shows you, out of the three states, the normal, the feedback, and echo sound, we're able to detect, out of there's about 6,000 normal sound, we are able to detect, mostly correct, with 5 mistakenly as echo sound, right? So that's nothing being mistaken as feedback sound. And for all of the feedback waves, there's a total about almost 1,200 audio clips that's actually labeled as feedback sound. And from this 1,200, we successfully, detected 1,154 of them. There are a slightly large mistake on the echo sound side, meaning for feedback sound we somehow predicted to be an echo sound. So that's a mistake. But there's only 5 of them being false labeled as normal sound. False detected as a normal sound. And for echo, it's a similar kind of accuracy, which is about total about 1,400 echo waves. We got about 1,357 correctly predicted, and we've got a split between normal and feedback sound. Mistakenly false predicted to be a normal sound and feedback sound with 20 of them. So it's around 96% kind of accuracy. So, any question on this slide?
Was the input audio target, categorized as normal feedback echo? Was it done manually, or was it done through some other tool, and that was given as input to the machine learning?
Yeah, so this is actually on the data collection part. And let's move to the next slide. That slide will give you some information on that. Keep going, one more slide. Next, yeah, okay. So to answer your question, right? So basically, we started the project by collecting about 45,000 audio clips. Each clip is 1 second. And the way we're collecting them is that we collect the audio waves. Some of them is actually just a normal sound, recorded normal. We sampled a lot of webinar recording, YouTube recording, and all this stuff. It's just normal sound without echo or feedback. But we also collected a lot of sound clip with feedback in there. And we intentionally make sure that we cut those audio clips with 1 second as 4 of feedback or 4 of echo, as much as possible. And to answer this question, we did a completely manual process, and it's a really tedious process. But this is also one of the most challenging issues in many machine learning projects, which is it takes a lot of money and resource to actually get the accurately labeled data, and we are not exception. We went through the same thing. Does this answer your question?
Yeah, thanks.
All right, great. So yeah, so this is how we collect the data. And the one thing I want to mention here is that we really don't have that many feedback data and echo sound. Even it's a limited resource. So we did a little bit of creative here. We created like about 1,000 or so, but that's not enough. In terms of the data set. So one of the things we did is actually we do augmented data. We're using some really fancy audio processing tools to generate different variations, like distortions of the sound, to make it like a feedback or echo. And this way, we're able to triple or even 4 times our, the manually generated data to come out with a decent size of the training set to be useful. Okay, next slide. And top. All right, so a little bit background, right? So in order to do this machine learning project, I personally learned a lot on the audio processing side. There's a lot of digital signal processing knowledge you have to accumulate to do it. But you can experiment with the product without, knowing it. But I just slide a little bit of background on this. Audio data. What is really audio data, right? So the original audio clip is basically a 1 second long sound wave. And so the so-called sound wave is a continuous signal, analog signals. But with with computer, the sound wave is actually digitalized. And this is done through a digital sampler. With that, the sound wave can be sampled at a particular sampling rate, and the result is a sequence of discrete time signals. And this is what we call samples. So, for example, on the Mac, the original audio waves are sampled by default with 44,001 kilohertz, that kind of sampling rate. Meaning, for every single second, you got a 44,100 sample data point. So that is the original. If you don't do any process, that's what you get. Obviously, this is a lot of data, and as I mentioned earlier on, out of this 45,000 audio clips, they're all 1 second audio, right? Which meaning that every single training example, you have without any pre-processing, you got a 44,000 features. That's a machine learning concept, right? Features used to train. You use the feature to train the model to get prediction. So with this kind of a large feature set, there's a few implications. One is actually it's going to be very, the data set will be huge, right? It's going to be very expensive to train and take a lot of compute resource. And secondly, it is going to be required. With that many features, you really need a multiply of that in terms of your training the count of the training examples. So you need a 44,000 times at least 4 or 5. That's like almost a 250,000 record you have to get, which is going to be difficult. So what do we do here is that we notice that for detecting feedback and echo, it's really not an art, right? It's pretty obvious. We found that we experimented to do a sample reduction for that originally sample data. We did a sample reduction down to 8,000, and for human ears, 8,000 sample rate, it is still very obvious. Like you can tell this is a echo sound, that is feedback, and that is normal. And learn from that, we got the implication to me is that if human can tell it, then machine learning model will be able to do it. So we made it, based on that opposition, we used the MPEG. It's open source tools from we downloaded, and we did a sample reduction for all the 45,000 audio clips, and made it a sample reduction to 8,000. And one thing I want to mention here is that why 8,000 is I also experimented with the next grade, which is 4,000, and at 4,000, I started to realize even as a human, I started making a lot of mistakes to misdetect, an audio clip to be normal or feedback, and that is the stopping point. That's why we decided to just 8,000, to get the balance of the accuracy and the efficiency. Any question on this? Okay, so this is basically a background on the audio data part. So Wentai, if you can go, move to the next slide.
Okay.
So one question was, were you looking for some particular accuracy rate with the different samplings values?
Yeah, when I see when I see sample rate, I did just as part of this project, so I did all kind of experimentation. So I started testing with a sample rate at 2,000 and 4,000. And when I say testing, I developed the model, with one of the tools we have called a data robot. And what I mean by accuracy is that when I use those machine learning tools to actually do quick evaluation with those data at the 2,000 sample rate or 4,000, I found my prediction that the model accuracy is rather low. So it's only like 60 or 70 or 80% kind of accuracy rate to predict it is a normal sound or it's a feedback sound. And I found as I increased the sampling rate to 8,000, I got a much better accuracy, which I'm pretty happy with. And I experimented with 16,000, like doubled 8,000, and I found my accuracy rate is pretty much stalled. Right, there's no further improvement. So that is basically there's no science here. Right? So the trick here is that I did all kinds of a lot of quick conducted a lot of quick evaluation, and let the result to tell me what is a more appropriate trade-off. Does this answer your question?
Yeah.
All right, great. So yeah, so actually your question is right to the point. This is the one thing I want to talk about, which is called feature engineering. And so on the slide I mentioned 4 choices, but in real life we actually did way more testing than more than this 4 choice. But let me just speak for this this 4 choice which I did a more serious study with. So number 1, we just used the original sampling data. So this is actually the digital sampler collected data, as I mentioned earlier on. And even with the reduction, you got 8,000 data points per second. And beyond that, we did a lot of research. We did a lot of reading on the audio processing papers. And one of the things that a lot of paper is talking about, this concept called audio features. So audio features basically some kind of digital signal processing result. You basically apply a Fourier transformation against the original sample data, and there's all kind of different transformation you can do on that. And the result of those, without going too much detail on the digital signal processing side, is that there are different forms of audio feature that are capable of predicting the some characteristic of the audio waves. For example, some audio feature is capable of telling you the type of the sound, whether it's actually a conversation, a dialogue, or whether it's music, whether it's some specific instrument sound, things like that. So there's all kind of different audio features with years of research from academic, with people from academic background. There's a lot of paper on that. We are certainly not expert on that, but inspired from that, I thought I might be able to use all those audio features to predict the type of the sound. Right? They probably speak to some degree, what the sound looks like, right? So that's how I got inspiration. So, but then again, we actually did some research on what kind of tools I can use to extract audio features from the original sample sound. And one of the popular tools is called Yafi. And using Yafi by default, you actually, Yafi support generating like 29 popular type of audio features. And now here we actually another question we have for ourselves, which is that without being an expert on digital signal processing or audio processing, right? We really have no clue of which one of these 29 audio features would be useful for us. So again, right? So the trick we played early on it apply here again, which is that without being an expert on the audio processing side, we say whatever, right? I just generate all these 29 audio features using Yafi. And I put them on the, in the training side with basically a lot of features, a lot of columns, right? And I just generated the gigantic training set with a gigantic number of columns, which is features, and just throw that into our machine learning tool called Data Robot, which I will give you a quick show later. So the beauty here is that you don't really care, which feature will be predicted. You let the testing to tell you. So we did one round of testing with all the features in Data Robot, and after that we did another round of testing with we did some feature impact analysis with Data Robot, and it will show us the top 30 most impactful audio features. And from those audio, so we did then we narrowed down, instead of using with the 29 audio features, each individual feature actually have anywhere from 40 to 200 different data points. So you actually end up with quite a few thousand data points, not much less than the original, 8,000 sample data. But so which is pretty expensive to train. But with the 30 most impactful audio features, this is actually the one thing that you're easily confused here is that these 30 is not the 29 type of audio features, but instead it is 30 different data points from a few collection of those audio features. As I mentioned early on, these 29 audio features actually have a few thousand data points. So, but with the feature impact analysis, we're able to nail down that there's only 30 of them are very impactful. So we did another round of testing with only 30 audio features, which is a much smaller data set, and we found a similarly accurate result, which is really pleasing. And further, from the 30 most impactful audio features, we found there's a lot of occurrence for this a particular feature called OBSIR. It stands for octave band signal intensity ratio. It's a pretty a weird name, but it basically, actually I don't know what's the science behind this feature, but what I do know is that this particular audio feature have about 49 data points, and there's about 15 or 20 of them shows up in this top 30 most impactful audio features. So that drives me to think that, to speculate that maybe this particular type of audio feature called OBSIR are very predictive of the nature of the problem we are talking about here, which is feedback and echo and normal sound. So again, I did a quick evaluation with only OBSR audio features. There's 49 of them, the data point, and I found even better and more efficient training than the 30 most impactful audio features. And the result I showed you earlier on, 96% accuracy, is all based on this. And all this testing shows me that, you know, the point I want to tell folks is that you don't have to be expert on to know what audio features can be predictive. You can actually just do a massive and very quick testing with the data, and let the training, the result, to tell you what is good. And so what you really need here is that you need really a good tool to help you do really quick repetitive testing, so that you can actually throw away all those data that's not very useful and then quickly nail down to the predictive set of the features that's useful for your target state, useful to predict your target state. So that's the lesson we learned here, and that's the experience we want to share with folks. Any questions so far on this slide?
What is the time that you took to do all this study and finally decide on this is the features that I'm going to focus on? How much time it took?
Well, the project time is, I couldn't quite tell. Maybe we did about a month or so, not necessarily 4 times, because we have other work to do. But I'll show you a tool. So, you know, let me switch to that. Okay, actually on this one I need to present. So that'll be a bummer.
It's okay. I'll give it to you. I think you just use phone for audio. Then you can still do screen sharing, right?
Okay.
Let me.
Should be. Yeah, that's right. Yeah, give me the.
Let's give it a try.
Yeah, pass me the presenter role again. Right, I should be able to present. Right, we should have been like that already. Let me see. Okay, so you can see my screen, right?
Yes.
So, good. So yeah, so this is the tool that I mentioned quite a few times early on. It's called Data Robot, and it is a tool that, you know, it's very popular among machine learning engineers. And so basically, what you do here is that, you know, you can actually create a new project. And let me just simulate that. I do a new project. Yeah. So what you do is that, you know, you can drag your training set, the CSV file, into here. There's other data sources that support, but I never tried. You know, ODBC, HDFS, URL to a S3 bucket. You can try all that. But so far, I only tried all local files. So without creating a new one, I just go back to a project that I already did, which is this one. So basically, for this project,
can you make font bigger?
The font is bigger. Sure, let me make it big, and let me maximize the screen. Is this better?
Yeah, a little bit better. Make the font a little bit bigger.
Okay. Okay. So as you can see, this is the project I created with the. This one is actually using less than the 45,000 the data point I mentioned earlier on, because with the license we got with Data Robot, we can't load large enough data. So in this project, I only have about 12,000 audio clips. And total features, 3,361 features. So this the so-called total feature are that machine learning, you know, the training set, the actual feature on the column. And this is the combination for all the audio feature we extracted with Yafi. And you can see here that for all those audio features that are of the same type, like in this case, the one you see on the screen is AM, right? AM_14, for example. It's actually one type of audio feature extracted by Yafi called altitude, I forgot what the M stands for, magnify or something. Basically, it is, I think, the signal intensity of the signal. So in this case, you can see for this one type of auto feature, Yahoo features, you got about 206. No, you got about, actually I don't think there's all of them. You got about 100, I think it's 100 data points. So with all these 29 auto features, you end up with 3,000 of them, right? And how do we do to answer the folks the early question? So what I do here is that in order to have a really quick evaluation, I create a project by dumping all these 3,000 data points there. It's the first step. And then I do a lot of evaluation I don't have to use all of them. Well, one of the key, really cool features from Data Robot is that I can just select, the feature that I wanted, maybe as a result of a feature impact analysis. Let's say there's 4, right? For example, somehow the feature impact analysis tell me these 4 features that I selected here are the most impactful feature. Then I can do a drill down experimentation with this by saying, create a feature. Here I can say create a feature list. Let's say test with 4 AM features. That's the AM data point, for example, right? I can do that, and I can create a particular feature name with that. And then after I do that, I could actually go to the models and just do create a new testing. Let's say I'm picking one of the testing I already have with a good result. Let's say a gradient. Actually, it doesn't matter. Just for the sake of demo, I just pick one, and I can use the feature that I just created called. Maybe I didn't save it. Yeah, I saved it. So test with 4 AM data. So when I do that, I can just say add a model. And once I do that, I can just do it. It will start the training. As you can see on the right, the training started. And I did a lot of this similar kind of experimentation by picking a small set of the features from this whole set, and then pick a model from the previous training that I found promising, and just iterate on this. So I can change the model, I can change the feature set, and after you can see this is very, very quick. And after a few rounds of testing and a drill down, you quickly come down to the conclusion to get an idea of what feature is more predictive, is accurate and efficient. And to give you an idea about how this efficiency means. So one of the tabs is called speed versus accuracy. So it's a quick dashboard to show you the performance of all the model I trained so far, and it will show you which model is actually scoring very high here, meaning very accurate. And if those models show up on the left side, that means they're very efficient. They train very, very fast. So, for example, this model is what is this one? This one is one of the gradient booster tree with probably a lot of features. These actually shows pretty good accuracy, but it's a very slow training. Take a long time to do it. So your objective is to try to find something that is very accurate and also on the left side, very efficient to train. So that's a very useful dashboard. You can also see from the learning curve. Well, this is not a good product showing the learning curve. Some other product will show you. You can see how they actually program. The accuracy improve with as you introduce more sample, your sample size go up. So you can get an idea whether it is still effective to generate more training data to make the model more accurate. So I only touched the surface of the Data Robot, but hopefully this gives you an idea of that. This tool can be really used to conduct very quick experimentation, so that you don't have to worry too much about what is a creative feature, what is a more predictive one. You just throw the data you collected into the Data Robot and let them to do the testing, and let the testing result to tell you what is good. So any questions so far on this one? On Data Robot or anything else?
Quick question on, see, you are doing one of the classifier test here. So can you do parallel testing for multiple algorithms to check which one is giving more accurate result?
Yeah, absolutely. That's another the thing great for Data Robot is that you can actually you don't have to wait. Like I just did the testing with 4, right? Oh, okay, these are already finished actually. I mean, if you have an idea, say I want to test with this 4 and with the 8, you can actually simultaneously doing this while they're doing the testing. You just submit another one, so you can have a lot of models simultaneously being trained, and that is very beneficial. And that's how you get, result very quickly. Any other questions? Okay, if not, let's go back. So let me see where we're on the slide. I think slide part of it almost done. Yes. So let's do a quick walkthrough of the project. We're all engineers here, so we can do a little bit hands-on here. So the project, we have a pretty detailed page, wiki page, to try to walk you through how to set it up and replay this. And one of our objectives for the representation is for folks to be able to, look at the page and download the code from Bitbucket, download data from our, really early version of the data machine learning data set, and do experimentation on your own. You should be able to do this on your own completely, but feel free to let me know if you're stuck somewhere. But let's quickly go through this page. First of all, we have a pretty detailed onboarding page. Right, as a README file in the in the Bitbucket. So this is what tells you, this the README file gives you the idea about what kind of prereqs that you need to set up. So as I mentioned here, you need to set up, you need to download this third-party tool called Yafi. This is the only piece that I consider a little bit challenging in terms of onboarding, because Yafi it requires a manual step to get it installed on your Mac. And if you're using a Linux box, it's a little bit tedious to set it up. But hopefully this page gives you all the information you needed to get it up and running on your platform. And we did use the test this on both Linux, on Mac, and on Windows. So another tool you need, as I mentioned early on, is called is FMMPeg, which is used to do a sample reduction. So with that, you should be able to get all your project, and then you download the code from Bitbucket. You should be able to get started. And one thing that I want to mention also here is the machine learning best practice. So this project, the representation is actually also conducted in such a way that try to follow some well-defined machine learning development guideline that we established here, which is about make sure your machine learning project is on the Bitbucket, not just a spreadsheet or not just something R model on your own machine. Make sure the data set you have is actually collected in the RMI machine learning data set, which is a collection of S3 file on a particular location that we publish. You can follow this link to put your data over there. Another thing which I repeatedly mentioning is use data robot to do a quick and dirty model and feature engineering experimentation before you do actual coding. This is a really, really useful tool, and I highly recommend folks to give it a try. And if you need access to it, you can send an email to Andrew Greenhut at alogamy.com for access. So that is the tools, and that's how you get onboarded. And feature engineering, I already spent, we can quickly go through this. I already mentioned earlier how we actually been able to start with the sampling data all the way down to a very small set of the feature called OBSR, come up with a model that are very accurate, right? So that we already talked about, so we don't have to go through this again. One thing I want to mention is the model performance. You can see from the data robot is let's just pick a model, the one that we have with OBSR. So yeah, this one. So this one shows you that with OBSR, as I give a specific name, called the job name called OBSR, and we're able to get about a validation accuracy of 99%, and the holdout, which is a testing set, also similar at 99%. And if you click on it, you should be able to get into the dashboard for performance. You can see the precision, the recall, the ROC curve. As it shows me, initially, data scientists on our team kind of mentioned to me that this seems to be not quite right because it's too accurate. But I doubted myself, but we did a lot of testing that seemed to be okay. And what I can the conclusion I draw from here is that it's probably just because for human ears, right? The feedback and echo sound is just too obvious, so there's no room for mistake. I hope that's the case. At least the testing results show so far is showing that that's the case. So So that's about it. And we have about 10 minutes. Let me do a quick demo of the UI that we have to give you an idea how this would work. So we developed a very quick UI with Python using the Python GUI. And so in this demo, I just loaded a pre-recorded WAV file, and there, in the intermingled with feedback and echo sound in there. Actually, there's no echo sound. This sample is only about feedback. So let's just play it. But I don't think you can hear this. Right, I don't think you can hear this. Yeah, so that I probably can't demo that. But the idea of this is that, as you can see here, is that while I'm playing the sound, when the feedback is detected, I visually, show it is the feedback detected. Basically, behind the scene, this UI application make a call to the model prediction API to ask, for every single second that pass, it will ask the model, say, is there feedback here? Is there echo here? And depending on the result, we will show the visually, to show you whether we detected. And unfortunately, I can't let you guys hear it, but otherwise you can see the feedback sound you hear from your ears are almost perfectly synced with the visual, which is actually the result of detection. Okay, so that's all for the presentation, and let's save some time for question and answer. Any questions? I'm waiting for the questions. Yeah, go ahead.
Hi, Peter.
Yep.
So, in a meeting, when the audience are speaking, so feedback may exist for a second. So our model should can able to recognize the feedback within that 1 second.
Yeah, well, that's actually a very good question, and it's a little tricky. So yeah, so from when we do the model training and the prediction, we're able to tell the presence of feedback even if it's only lasting for 1 second. But in real life, usually it's much longer. So what do we would recommend if we do have a chance to integrate this with the audio engine? The way we usually do this is that we're going to detect. from an application point of view, there's other considering you have to consider, right, to see how you effectively deploy this model. So the recommendation we made for the audio engine team is that they should actually make a call on the prediction API on the on the audio they collected consequently 3 seconds in a row. So basically do 1 second and then do another 1 second and do a 30 second. They only if they actually all this time will tells you that there's a feedback detected. It's a good idea to tell user that it is detected and do something more aggressive, such as signal suppressing, things like that, right? So this way you get a better confidence and without really losing any accuracy issue, because in real life you usually have more than 1 second of feedback anyway. So
okay. So is there any specific target that we are aiming for? Like if feedback is more than for 5 seconds, we were able to detect it and remove it in the output?
Very, very good question. Yes, so the detection part is actually what this reference is all about, right? But to actually put it in practice, to actually deliver real user experience, right? The improvement on user experience, we need additional work. But that is actually, those additional work will not be no longer machine learning project anymore. So basically, I talked to the audio engine team quite a few times on this topic, is that they can actually apply some kind of signal suppressing technology to smooth out the signals to make it less annoying or totally eliminating the issues, the feedback issues. And they still need this machine learning detection because they can't just apply the signal suppressing algorithm to the audios because it's too expensive. So the promise of this solution to them is that once we can detect, they can apply the suppressing algorithm, right? So this way, they're not doing that for all the time, and only do it when they have confidence there are issues in the audios. But this is a different effort, to do a digital signal on that is not machine learning anymore.
Okay, thanks, Peter.
Okay, any other questions? Okay, if not, I can also give you a very quick show of the. We don't have time to walk through the code, but you guys are engineers, so I'm going to give you a few of the notebook we have, which is yeah. So we have one notebook. It's called a feedback detection model pipeline, and without going into all the details, since you can actually just download this and start playing with this. But the notebook is a representation, so the way we try to show people how you can experiment using Jupyter Notebook with the data and do training. So with popular Python packages such as Pandas, NumPy, and scikit-learn, you can do a very easy machine learning project and do visualize your data like right on your notebook, just like the way I shown here. You can actually draw. You can actually put your data on a two-dimensional graph to see how it works. Like in this case, we show this is all the data we have. But after we did the training, I have even a very interesting data a graph to show you here, which is that you can see that we are able to categorize the audio data into two buckets. Right, those black points, the dark here are representing I believe the feedback sound, and the green one stand for the normal sound. So we're able to visually show you the boundary of these two sets of data very clearly. You can see there's some outlier here, but by and large, we can actually categorize them very very well. So there's some interesting thing you can play with the Jupyter Notebook and with the Python packages. So feel free to play with this notebook and see what it do. All right. Any other questions?
So Peter, question from me. So how would you mind explain a little bit, after you done experiment with data robot, how did you get the model into how do you implement continuously with Jupyter Notebook?
Oh, great. Yeah, I should have mentioned that. Great question. Thanks for reaching that. So I mentioned quite a few times you do data robot and let data robot do the quick iteration for you, right? But one of the problem with data robot is that it's a proprietary system, and they have a pretty tight grip on the model they have, and you really can export that. But it doesn't really matter, right? But most of these models they support are the very popular model that you can find all kind of imitation for those models, such as in scikit library from Python. So what we do here is that we use data robot only for the sake of quick iteration, to do a quick validation of our initial hypothesis, to understand the nature of our data, to know which model can do the job, right, and which feature can accurately predict the target state. So, for example, I'm just picking this one. So after numerous testing, I found the model called gradient boosted greedy trees with the feature that is OBSR data only is able to deliver a very accurate result with a very small feature set, meaning it's very efficient. Then all I need to do is that, thank you, data robot, I don't need you anymore, right? We come back to Python code. And what we do here is that we're using the Python implementation of a gradient boosted tree here, which is available from scikit library. And here's a line I'll show you. So basically, we just hand code that again. But writing code in machine learning project is never an issue, right? It's a very small piece of code. So what you need to know is actually what code to write, which model to use, right? So in this case, the part of the code that are doing the model and training, I believe it's right here, which I comment out. Yeah. There you go. So with this one, we have a gradient search cross-validation library from the scikit, and we use this one to do the training. And the model we picked is a GBM, so gradient boosted tree. So instead of writing Python code to try 20, 30, 40 different models, we just use the GBM. Why? Because data robot already tell me this is a very good model, and no surprise, when I write the code, the result is pretty good. So instead of writing code and testing with 20 models, we just write one. So Wintao, that answer your question?
Yes. I think we are right on time. Do you want to wrap it up?
All right. Well, thank you very much for spending time with us. If you have any questions, feel free to reach out to me or Wintao or to machine learning groups.
Thank you for attending. I have pasted the BDI Tech Talk wiki on the chat window. Feel free to copy that. If you have topics to submit to BDI Tech Talk, please do so on the wiki. And thank you for joining us today. Have a good day.
Thanks.
All right. Thank you, guys.
Bye.
All right. Thank you, guys. Bye.